Thank you very much. It's a pleasure to be here, and what we're going to talk about in this session is science and how the theme of today's conference fits into our thinking specifically as scientists. So I've already picked up some things that are maybe different for scientists compared to humanities from some of the things that have been said already this morning. One thing that struck me, I don't know whether it struck you in the same way, was the comment that as academics we have complete freedom over our time, we can choose when we work. Well, yes, I imagine if you're an art student that's true, but if you're a scientist, often our time is restrained by all sorts of things like experiments and things like that. So our experience of time as academics, as scientists, is naturally going to be slightly different, and that's why it's quite nice to have these parallel sessions where we can look at the issues a little bit more through the lenses of our science subjects. So as you've already heard, I'm a physicist, and so I'm going to talk about time from a perspective of physics, but also from a perspective of science in general. My research is in biological physics, so my research is in an interdisciplinary area. I've never studied biology, but I've learned a lot of biology through my research, thanks to very patient colleagues who helped me out. So I do have a reasonable feeling for how things happen within biology as well as within physics. So in that sense, I hope I can say some things that resonate with all scientists. So I just start by letting you know what I'm planning on talking about. So there's two main sections to what I'm going to talk about. The first is time in science, and the second is how do we use our time. So that's a little bit more practical, and that will be followed up more this afternoon, particularly, for example, in a panel discussion. So in terms of the first section, time in science, I'm going to talk a little bit about the beginning to the end, as in the universe, a little bit about the nature of time, and then I'm going to talk about different time scales that we come across in our scientific studies, and I've put there from attoseconds to billions of years, which is pretty much the time frame that physics spans, but obviously one person doesn't tend to span all of that range in their research, so I'll show you where my research fits into those time scales. So let's start with some grand thoughts about the beginning of time. Through what I'm going to say about science, I'm going to bring in where I think that things provide overlap with our faith. So in terms of modern cosmology, we know that time had a beginning. Well, that's actually quite significant, that time had a beginning. The Bible says that time had a beginning, that God created the world, that there was a moment of creation, that God created time. And I find it quite interesting that that's actually what science says today. So there's a resonance there between what science is saying and what our Christian faith says, that the time actually had a beginning. The universe had a beginning. There was a moment of creation, and the Big Bang was about 13.8 billion years ago. And that number is continually being revised a little bit, but as a physicist I tend to round things up, so I call it 14 billion. Anyway, so that's actually quite a long time ago. I find it difficult to get my head around what 13.8 billion years really means, because I haven't been around that long. But we're looking at a universe that has a very long history. And began a very long time ago, and in that sense we're really quite latecomers on the scene as human beings. If any of you don't recognise the logo in the corner, that's quite a funny American sitcom if you wish to watch it. I did once actually go into a school and to speak, and the teacher introduced me as a physicist. And there was one child who put up their hand and said, "What's a physicist?" And another child said, "Is that like Sheldon?" So I'm like Sheldon. Yeah. Anyway, that sitcom is called The Big Bang Theory, and this picture, by the way, is the all-sky map of the cosmic background, microwave background, that's taken by the WMAP, and it's one of the latest pictures of the universe in terms of the microwave background radiation, and that is what tells us something about the Big Bang. It's the leftover radiation from the Big Bang. So there's a Big Bang, and then actually it's sort of dispersed quite a lot, but this is what's left. And so this is one of the key pieces of evidence that goes into our understanding of the Big Bang. Okay, so that was the beginning. I'm going to now jump to the end. What about the end of time? So this graph here shows you different models for the cosmology of the end of time. So we're in this spot in the middle that says now. And going forward into the future, there's various different options of what could happen. I personally love the idea of a big crunch. But actually the current data doesn't support that one. The big crunch is that, well, there was a Big Bang and the universe expands, and then at some point gravity takes over and the universe contracts again, and you end up with a big crunch, which is the sort of opposite of the Big Bang. Actually, the current data pretty much rules that one out. And so the current data suggests that we're really quite close to the critical point between the universe continuing to expand forever or it contracting into a big crunch. But the current thinking is that the universe will continue to expand, but probably going towards a constant rate of expansion, which means that the universe won't end in a big crunch. It will more sort of peter out in what's called the heat death, or sometimes people call it the big freeze. So in other words, things will continue to expand until basically there's no energy left and everything sort of dies off because it's too cold. Anyway, the point is the universe will end in some way, which again is interesting because that's what the Bible says too. So I think there are some interesting parallels that you can think about in terms of modern science and cosmology and the Bible and the Christian beliefs about God making the world at the beginning and there being an end. Of course, in some senses, in our everyday Christian lives, thinking about the end of the universe isn't very practical because our personal end of life on Earth will come most likely a lot earlier than the end of the universe, and therefore when we think practically about the end of time, what that usually means on a personal level is our end of our life on Earth, and then you can think about what happens beyond. But it is fun to think about the long time scales involved and how might things end up in the universe, and more locally how things might end up on Earth. So I should say that beautiful picture of the stars there is from the Hubble telescope, and the Hubble telescope has really enriched us with some amazing pictures and astronomical data. Now, this idea of the heat death is actually related to what everybody calls really the arrow of time, and this is something important about time, and it was picked up this morning in a historical context where the comment was, well, we can't change yesterday. And actually the arrow of time is that time goes forwards and we cannot go backwards in time. And that makes time quite interesting and very different from space. Space we can go in different directions, we can go forwards and backwards. But in time we can only go forwards. Time only flows forwards. And this is why we can talk about a beginning and an end and going towards the end and think about the end times in that sense. That actually comes from the Second Law of Thermodynamics. So if you're a physicist or a chemist by background, then you would have learned about the Second Law of Thermodynamics, which basically means that the entropy of the universe is always increasing in an irreversible process. And so what that means is that there are certain things that cannot go backwards in time. So for example, the pictures I've got here, I've got a droplet of water that's falling onto a pond, and then in the right-hand side, you've got the ripples that spread out from that impact of that droplet of water. Now, you're not going to see the reverse happening. If you take a video of that situation and run it backwards, it looks completely wrong. You do not see, naturally, ripples coming together and then a droplet going upwards. And so that's an example of dispersion of energy, that the energy is dispersed and the opposite cannot happen in terms of energy coming together spontaneously in that sense. In a general sense, that can't happen. There are ways you can locally decrease the entropy of a system, but only if globally, in terms of the universe, the entropy increases. So for a completely reversible event, then the change in entropy is zero, but for all practical events, there is some energy lost, basically, and that actually, in some fundamental way, gives us the arrow of time. So that is why we can only go forwards and not backwards. So we've got this arrow of time, we live in time, we can only go forwards in time, we can't go backwards, we can't change things in the past. So this is also related to the end times, in terms of the end of the universe, because the heat death is also due to this second law of thermodynamics, that energy is dissipated and eventually dies away. There's another aspect of time from physics that I think is interesting and is sometimes interesting to think about in terms of our faith, and that is thinking about space-time as a four-dimensional coordinate system. I can't draw a four-dimensional axes on a two-dimensional screen, but I can try and draw 3 dimensions. So the axes I've drawn there, I've got time going upwards, and then I've got x and y and a plane, but obviously actually 4 dimensions is, you've got the 3 dimensions of space plus time. And so some people think about this 4-dimensional space-time as the 3 space coordinates plus time as a fixed thing, and that they imagine God outside of that and looking onto the coordinate system, and therefore for God he can see everywhere and everywhere in time as well as everywhere in space, and therefore God is sort of outside of time and sees the past and the future and the present all together. And this fits with the idea of predestination, and that might be something that you ascribe to, or it might be something you struggle with. Personally, it's something I struggle with, and I don't actually find this particular picture of God being outside of time and looking at the 4-dimensional coordinate space as helpful for my faith. And I will mention a little bit later on what I find a little bit more helpful. But I thought I'd mention this because this is something that some people find helpful. But as Einstein showed us, actually time is relative. So this is an interesting concept within modern physics, that time is relative. So what do we mean by that? What do we mean by time is relative? Well, in Einstein's special theory of relativity, the major principle that he discovered is that the speed of light, c, is constant. So the speed of light is a fundamental constant in the universe. And that actually leads to time dilation. Now, the physicists among you will know all about this, and those of you who aren't physicists probably don't know much about this at all. But basically, what it means is that if you travel very, very fast, time slows down. And if you like maths, then that's the equation and tells you how time slows down. So if your velocity v is very small compared to the speed of light, then delta t primed is basically the same as delta t. But if your velocity is close to the speed of light, then time slows down. Now, in our practical daily lives, we don't travel near the speed of light, and therefore we don't really worry about this. But if you were on a spaceship and you were traveling, then the time would slow down for you compared to somebody on Earth, and it all gets quite fun. And there's the famous twin paradox, whereby you imagine 2 twins where one stays on Earth and the other goes on a spaceship travel, and they end up being different ages and that sort of thing. But the point is that at this fundamental level, time is relative, even though at the level of our everyday lives, it's such a small effect that we don't really notice it. But that can give us some different ways of thinking about time from how it was viewed in the past. But there's another aspect of modern physics and its relationship to time, which I find really quite interesting. And that's when we start thinking about quantum mechanics. Again, some of you will have thought about quantum mechanics a lot before, and some of you won't. But what I'd like to talk about is the uncertainty principle in relation to time. So Heisenberg's uncertainty principle is often expressed in terms of space and momentum, but you can also express it in terms of energy and time. So it's expressed there in mathematics that the change in energy times the change in time has to be greater than or equal to h bar over 2. H bar is a constant. So what this says is that if you know the energy exactly, then you can't know the time exactly, and vice versa. So there is a certain uncertainty in the time. Now this can be difficult to get your heads around, so I think it's helpful to think about a very concrete example of this, which is spectroscopic line widths. Now if you're a chemist, you may well have used this in your own experiments to find out what elements you've got or something like that. So if you're doing spectroscopy on a system, you get a series of you get a spectra out, and the graph here that I've shown there is just showing an example where we've got the intensity of the light coming from your sample against frequency. And what I want to highlight here is that the lines are not infinitely thin. You get a broadening of the lines, and that is this lifetime uncertainty. So you see that big peak in the middle. Well, you can find the average of that peak, and you can find the point which is frequency, but there's a width to that line which shows actually you've got delta f there, you've got a range of frequencies, and that corresponds, that's 1 over delta t, the time uncertainty there. And so that's actually it's not an uncertainty, it's not an error in your experimental setup, it's a fundamental uncertainty in the frequency of the photon that is emitted. And that's due to this uncertainty principle. So that's interesting again. It's another modern physics concept showing us that our classical picture of time as being very much set in stone in this block of four-dimensional space-time, actually it's not quite as set in stone as that. We've got these modern concepts of time being relative in terms of if you're travelling near the speed of light. We've got the uncertainty in time when we're looking at very short events like spectra. And so you've got these kind of slightly more fuzzy situations. I don't know if you can see that vague blue blob on the screen, but that's my attempt to show that, actually there's some uncertainty in these things. So in terms of quantum mechanics, we calculate probabilities, and we can calculate the probabilities extremely well. But we can't predict within them for an individual event exactly what will happen. So this brings in this concept that things aren't so clearly predefined as we might previously have thought in classical thought. I personally find this quite helpful in my own thinking about faith, because as I said before, I hinted that I find the four-dimensional space-time picture of God being outside of time and looking on, and a very pure predestination view, I find that quite difficult in my own faith. And the reason for that is that I find that quite difficult to square with the mess of everyday life. And well, if God can see exactly what's going to happen, why doesn't he do something about it? Why does God sit back and just watch disasters happen and things like that? There's the opposite to predestination is free will, and this is a long-standing theological problem, and we're not going to solve it today. But We feel like we have free will. Do we really have free will? Is the future open? Does God know what the future is going to be in all its details or not? Does God know the outcome of the quantum mechanical events or not? These are things that I find interesting to think about and try and get my head around. I've put on the screen there open theism. If you're interested in exploring this idea that the future may be in some way open, such that God knows the big picture plan, of course, because God set the big picture plan, but maybe God doesn't know the outcome of each quantum mechanical event because that's not knowable. If you're interested in exploring that idea, look up open theism. I find that quite interesting. Some people find it quite controversial because it's sort of in contradiction to predestination, and how do you bring those two things together? And that's one of the challenges of thinking theologically. And you've got this paradox there. But as scientists, we're used to paradoxes, especially physicists. Wave-particle duality, that's a paradox. This is another kind of paradox, and if you are comfortable enough with paradoxes, I'd encourage you to think more about that and what it means for your own faith. But I'd like now to move on to something that will make the biologists feel a little bit more comfortable, because I've been talking about quantum mechanics and relativity and these sorts of topics that physicists are comfortable with, and on the quantum side some chemists are comfortable with that. But what about biologists? Let's talk about evolution. Evolutionary timescales are long. So the Earth is 4.5 billion years old, and the first life on Earth appeared about 4.2 billion years ago, which is actually not that long after the Earth started, although actually billion years is a long time, but yeah. Homo sapiens, on the other hand, only appeared roughly 200,000 years ago or so. But that's still a long time, especially when you compare that time to claims from, for example, young Earth creationists who say, well, the Earth is about 10,000 years old. Well, if the Earth is about 10,000 years old, you can't have Homo sapiens first appearing 200,000 years ago, and that flies in the face of the scientific, geological and astronomical data showing that the Earth is 4.5 billion years old. So that can be a challenge to those of us who are scientists and accept the science, and we accept geology and radioactive dating, and we accept the biology, and evolution just makes so much sense. There's many things in biology, and we can watch it happening in the lab. We unfortunately see it happening in our own bodies and those of patients around the world who are suffering from antimicrobial resistance as the bacteria evolve. So we see evidence of all of this around us, but then how do we engage with those Christians who disagree with all of that scientific evidence and hold on to young Earth creationism? And that's quite a challenge. I don't know where you stand on that, but I'd say that what matters here is not so much the science, but how we interpret the Bible. Now, I personally don't have a problem with accepting all of this science that doesn't contradict with my faith, because of the way that I read Genesis. I don't read Genesis as talking about 6 times 24 hours. I read Genesis as the message being God created this world and saw that it was good. And a beautiful poem describing how God created, but not a scientific textbook telling me precise details like how long it took and what happened when. But some people do read Genesis in that sort of a scientific textbook way, and therefore find contradictions between Genesis and the science. And how do we engage with those people? Well, actually, a lot of what we're talking about today is how do we engage with people who have a different worldview from us in terms of not a Christian worldview. How do we engage with our scientific colleagues who aren't Christians? But sometimes there are challenges of engaging with our fellow brothers and sisters in Christ if they come from a different perspective from us. And I think one thing that's very helpful to remember in any of those engagements is that if you're an evolutionary biologist, you're doing a PhD in evolutionary biology, then it really matters to you what you believe about evolution. But if you're talking to somebody in your church who has a very different kind of job, It doesn't matter what they believe about evolution. And in our conversations with people, we need to respect where other people are coming from. And we shouldn't get too much on our high horse about an issue that doesn't actually matter to their lives. Hopefully, they will respect us as we respect them, and we'll see that for us that is an important issue. So that's an example of something whereby people have different views. Occasionally you find people who are evolutionary biologists or who are studying biology but actually have a personal problem with that themselves, in terms of it's a personal crisis of faith or contradiction to their faith. And if that's the case, then I think it is worth thinking through these ideas, because it is something that matters to you, because it's a conflict between your work and your faith, and therefore it is worth resolving. But for many people in this world, they don't need to resolve that issue. They can be fantastic Christians without worrying about what they believe about evolution. What I do think is important when we're talking about these sorts of things is for young people who are interested in going into science, or who, whether or not they're Christians, they're interested in going into science. For some of them, this can be a stumbling block and can cause them to not go into science or to not be a Christian. And I think for those people, it's important to explain to them that there's a variety of different Christian views out there. There are some fantastic Christians who are young earth creationists. There are some fantastic Christians who are theistic evolutionists and who believe in evolution and that God made the world through evolution. And there are people who believe that God made the world in 6 times 24 hours. And that's fine. We differ. That's okay. We're still Christians together. So I'd like now to spend the next few minutes talking about timescales in science. So I've put a few timescales there in scientific notation in terms of seconds. So 10 to the 75 seconds, and then you'll see that the timescales get shorter as I go down the page. So 10 to the 17, 10 to 15 seconds, 13 seconds, 9 seconds, 10 to the 5 seconds. I'd like anybody to guess what sort of process in science happens over 10 to the 75 seconds. That was the longest I could think of. Anybody like to guess? This is the bit where you can be interactive. If you're not sure, you can guess as 10 to the 75 seconds. Maybe you can guess one of the other numbers on this slide. Anyone like to throw something out? Something that's really long?
Like the time for the black hole to form?
Oh, pretty close. This one is the time of evaporation of a black hole that's 1 solar mass in size due to Hawking radiation. How long will it take to evaporate? 10 to the 75 seconds is actually longer than the age of the universe. 10 to the 17 is the current age of the universe. 10 to the 17 seconds is 13.8 billion years, roughly. These are all order of magnitudes, which is fine as a physicist. Some scientists have to be quite precise with the numbers, but if you talk about these big numbers, order of magnitude's fine. Okay, I've got a bit of a clue in the picture on the slide here. What's the next one? Not quite, it's Dinosaurs Extinction. So the dinosaurs became extinct 66 million years ago, which is about 10 to the 15 seconds. 10 to the 13 seconds, anyone like to guess that one? This is why we don't normally use seconds for these sorts of things. That's 200,000 years, the age of Homo sapiens species. 10 to the 9 seconds. As you can see, we're getting smaller and smaller, so we're getting a little bit more tangible here. Anyone like to suggest what 10 to the 9 seconds corresponds to? We've gone from the billions of years to the hundreds of thousands of years. This is quite a test of our order of magnitude concepts, isn't it?
Oh, lifespan.
Excellent. So human life expectancy. About 70 years, about 10 to the 9 seconds. 10 to the 5 seconds. That's a day. So this is why we talk about a day rather than 10 to the 5 seconds. But okay, so this slide summarises going from a day, which is our everyday human existence, to the longest timescales that we know of in science. And I find this staggering. And it leads me to awe and wonder. I look at numbers like that, I try and get my head around how long the universe has been around for, how long humans have been around for, and I just find that really inspiring. And as a Christian, seeing something in science that's inspiring leads me to worship. But you can go smaller. So we're going to go smaller still. Okay, so does anyone know how long it takes for light to reach Earth from the sun? In minutes, that's fine. Anyone know? 8 minutes, very good. 8 minutes. That's interesting to think about as well. You know, the light we see from the sun, it actually left the sun 8 minutes ago, travelling at the speed of light. So that gives us an idea of how far the sun is away from us. Okay, 0.1 second. We're now going smaller than a second. A tenth of a second. What happens in a tenth of a second? Anyone like to guess? Blink. Excellent. A blink of the eye. Tenth of a second. Okay, 10 to the minus 3 seconds. We're now getting much more into the realm of biology. So this is a millisecond, and it's about the time of a neuron firing. Okay, a microsecond. Anyone like to suggest what might happen on a microsecond? I'll give you a clue, it's a biological thing. The conformational change of a protein. Now that's thrown in there because I thought a lot about conformational changes of proteins during my PhD. These days my research is at slightly larger length and timescales, but microseconds conformational change of a protein. Okay, what about a nanosecond? Well, this is a bit of a cheat. A nanosecond is how long it takes for a 1 gigahertz processor to cycle once. Well, that's a bit of a cheat because 1 gigahertz is, by definition, 1/1 nanosecond. But that gives you an idea as to how fast your computer's working. What about picoseconds? Any chemists among us? How long does a chemical reaction take? So a chemical reaction transition state can have a lifetime of about a picosecond. But we can go smaller than that, even smaller than that. So femtoseconds, 10 to the minus 15 seconds, that's the cycle time of UV light. And that's really relevant because we can now make femtosecond lasers and do some extremely fast experiments using femtosecond lasers. But actually, the shortest laser pulse to date is on the scale of 10 attoseconds, so that's 10 to the minus 17 seconds. And I was astounded in speaking to a colleague last week about her experiments that she can do with attosecond laser pulses, and I was just astounded that she could get information on such a fast timescale. What is the final one, 10 to the minus 44 seconds? Any physicists like to suggest what time that is? This is the shortest time known, as it were.
Is it Planck time?
Yeah, it's the Planck time. Thank you. So I've gone from the longest scale to the shortest scale. Again, this leads me to worship. It leads many of my non-Christian colleagues to awe and wonder. But they don't have anybody or anything to attribute that to. For me, when I see something like that and I say, wow, this universe is amazing, look at what we can find out about it through science, by looking at these different timescales and getting data from the different timescales. That's amazing. That leads me to worship. And that's one of the things that I find a little bit sad about my colleagues who don't worship God, that they don't have anybody to attribute this wonder to. And in fact, the wonder that we experience in science is something that does point some people to faith. And that can be a real talking point with our non-Christian colleagues about our response to the amazing things we see in science, because that's something we share with them. They also are amazed at the things in science, and so that's something we can share. I'd just like to make a few comments about things that are relevant to timescales in the practice of science. Now, physics, which is the science I come from, has been very successful by separating timescales. So in many areas of theoretical physics, we can calculate things by considering just one relevant timescale. So for example, we can identify fast and slow variables and average over the fast ones, and then solve something just for the slow variables. An example of this comes from meteorology. So the graph you see there is actually the global average temperature from the Met Office and against years. And you can see that there's lots of ups and downs. Those are the fast variables. So, for example, there's the yearly changes and the seasons and all of that. And there's lots of fluctuations, lots of things happening on the fast time scales. But if you're interested in climate change, then what you want to know is the global trend over a longer period of time. So you can average over those fast things that are happening and look at the overall slow trend, which is very clearly upwards, taking off from the Industrial Revolution, which you might not be able to read the years there, but the increase in gradient corresponds to the start of the Industrial Revolution. So that's an example of where physics can be quite successful by focusing on a particular timescale of interest and averaging out the other ones. Something I find very interesting in my research that is from a physics background but thinking about biological problems is that that separation of timescales that physicists have relied on so much is quite difficult to do in biology, because often you have quite different timescales that are important and at play in a particular system in biology, and you have interdependence between timescales. So you have something happening on a longer timescale but is influenced by something happening on the shorter timescale and vice versa. And so you get into all sorts of interesting issues with taking stochastic processes and bringing them up to the macroscopic events, and you can't always do the same kind of averaging as you can in physics, and that makes it quite interesting and challenging. Now, I'm conscious of the time, so I'm going to speed up a little bit, but I couldn't resist mentioning something about the epoch that we're currently in because of the graph I chose to illustrate my previous point. So this is climate change. So if you think about ages of the Earth, there's a lot of people now claiming that we have actually reached a new epoch or age in the life of the Earth, which is an age that's dominated by humans. And actually the sad thing about that is the way that it's being dominated by humans is quite negative for the planet as a whole. So we've got major challenges with climate change, pollution, mass extinctions, and I think this is a major issue for Christians, because what does the Old Testament tell us? What does Genesis tell us? What does God tell us? That we should be stewards of this earth, that we have the responsibility to look after this earth, and therefore that's something that is a real calling for Christians, and particularly for Christians working in science areas. Whether or not one of these major issues like climate change or pollution is your research field, I think we all have a certain responsibility to think scientifically and biblically about these global challenges. Last few minutes, I'd like to switch gear a little bit and talk about the practicalities of how we use time. So do we use time sustainably? We know that we're supposed to be using the Earth's resources sustainably. We need to think about our carbon footprint. We need to think about how we're using resources. But what about thinking about time as a resource? Are we using time sustainably? I think this is a major challenge for academics and particularly for PhD students. Are you burning the candle at both ends? Well, we all do at times. But is that sustainable? Are we using time sustainably? Are we wasting time like we waste the Earth's resources sometimes? We waste food by letting it go off. Are we wasting time and not using it in appropriate ways? Do we save time? Are we being efficient in our work? Or are we exploiting time and using too much of it to the detriment of our health or of our endurance? Are we using time wisely? Maybe if we start thinking about time as a resource we should be using sustainably, it will help us in our everyday challenges of making those decisions as to whether we push on and try and get something finished, or do we call it a day and get some sleep and do it the next morning when we're more fresh. I'm continually astounded at the times when I give up, completely frustrated that I can't solve a problem. I give up, and then the next day when I'm fresh, I solve it quite easily. And despite the number of times that's happened, I still find it hard to remember when I'm struggling with something the night before that actually it's more sensible to give up and try again when my brain is fresh. So these are the sorts of everyday lessons we have to deal with. This clock here that you've seen on some of my slides, I chose because it stopped, and it stopped at 20 to 12. That's significant for me because I'm a lecturer, and our lectures always finish at 10 to the hour. And I had a clock in a lecture theatre just like this one that stopped at 20 to the hour, which was absolutely fantastic because it meant I always had 10 minutes left for my lecture. My students didn't appreciate it, but I always had 10 minutes left. Sometimes we would wish the clock to stop to give us more time, but I think we need to think carefully about these things. How many hours do we work? When do we work? I think this is a real challenge for us as scientists, because the general view around us is often that science is a hobby. We do it because we love it, and therefore there is no distinction between work time and hobby time, because science is our hobby, so we do it all the time. And we end up actually working all the time. And that might be okay for a couple of years, might be okay for the whole of your PhD. But at some point, and that point comes differently for each human being, you're likely to burn out. It's not a sustainable use of time. But how do we counteract that view around us that science is a hobby and that therefore we do it all the time? We need to recognise that we're human beings, we're not machines. We may work in a science lab, but we're not machines, we're using machines. But we're human beings, and we need to think carefully about how we use our time. Now, in contrast to the arts PhD students who can work whenever and there's complete freedom, often science PhDs are much more like a job. We're expected to be there at certain times, and the experiments often have to happen in working hours or office hours, depending on what the experiments are. And so we can treat it a bit more like a job. But that's only in one sense. In another sense, we can't treat it like a job at all, because there's certain experiments that have to be done out of hours. What if you're an astronomer? It has to be done in the dark. What if you're a biologist using animals that need to be fed, even on Christmas Day? There are expectations on our times that don't fit into a 9-to-5 job. And we need to recognise that and learn how to deal with that. And that's okay, as long as we get rest time. And as long as we give ourselves rest time. The Bible is very clear, the Old Testament is very clear, and the New Testament, about this concept of Sabbath. When I was a student, an undergraduate student, I listened to a talk by Michael Green in St Aldate's Church in Oxford. And he talked about the Sabbath. And he started by saying, are you stressed? Are you tired? Are you overworked? Are you anxious? Are you worried? And I was like, yes, I'm an undergraduate student at Oxford, of course I am. And then he was saying this, and then he was, do you take a Sabbath? From that day on, I didn't do any work on Sundays for the rest of my undergraduate degree. That was a challenge, but once I got used to it, it was so freeing. It meant I wake up on a Sunday morning and I wasn't going to do any work all day until the Monday. It was wonderful. And I had friends who found it it turned out to be quite a talking point. You know, they were astonished I could do it, you know, people who are working all the time. And I was saying, well, actually, I'm more efficient the rest of the time because I have Sundays off. So actually, finding a Sabbath for yourself can be more efficient than working all the time. Now, I think it's perfectly fine to use the word Sabbath flexibly. It doesn't need to be Sunday, but it needs to be time where you can rest and sleep and be a human being rather than a human doing. Now, I'm preaching to myself here as well, because I use this phrase because it's what my sister tells me all the time. She's a clinical psychologist, so she understands about people. I'm a physicist, I don't. And she says to me, Rhoda, you're being a human doing, but you're supposed to be a human being. Sometimes I just do, and I forget to be. Well, what can we do when we choose to be a human being? Well, we give time for God. We can pray. We can rest. In some senses, I think time for God is not a separate category of time that we put in our diaries. It can be. I'm going to church at that time. That's something we can put in our diaries. But time for God is all the time. Sometimes I find the most helpful place to pray and time to pray is when I'm going to the toilet. Why? Because as a human being, I have to do that regularly, even when I'm at work. So I can have a prayer break whilst I'm having a toilet break. It's great. Our workplace, our science, our discipline is a mission field. We are giving time to God whilst we're at work, whilst we're doing our science. Or we can be, depending on how we view it. So we have issues with time management as scientists. We've got lots of things to juggle. We've got a balancing act, prioritization, things that are urgent and important. All of these things we have to deal with. But there's something else that as Christians I think we need to think about. And that is, do we use our time generously? When we think about time as a resource, actually, our time's not our own. It's a gift from God. We've been given this resource. How do we use it? Do we use it all for ourselves, or do we give it to others? Now that includes our work time, our social time, our church time. I'll give you an example of something that happened to me about a week ago. I was going to the toilet. Actually, I was on my way back from the toilet to my office, and I came across a PhD student in tears. Not one of my own, but one from my department who I knew. And I could have rushed back to my office and not noticed her. But I had a split-second decision, and I thought, no, I'm going to give a bit of time to her. So I stopped and I said, do you want to be on your own, or do you want to talk? And she shrugged her shoulders in a kind of dismissive way, which meant I thought, well, she wasn't going to kind of, kick me out. So I sat down with her and I talked to her, and I said, what is it? Oh, doesn't matter. What is it? Is it work, or is it outside of work? Work, she said. I'm stressed. Well, then the story poured out. She had to get her poster for a conference printed the next day. She just received some feedback from someone, I assume her supervisor, but she was too polite to say, with loads of things she had to change, and she was very stressed because she didn't have time to do all these changes. She had to get it printed the next morning, and how was she going to do it? And she wanted to sleep tonight. She didn't want to do an all-nighter. What she was going to do? And I talked it through with her, and I said, well, what if this person gave you the feedback tomorrow after you'd printed it? It'd be too late. And so together we decided which were the most important changes that needed to be changed, and she agreed she'd change those and forget about the rest, because actually we can't have perfection and sleep. So that's an example of a situation where I, in a split second, decided to give someone else a bit of my time, and actually ended up helping her to use her time wisely. I'd like to finish by quoting from one of my favourite passages in the Bible. It's in Ecclesiastes, and it's not on the screen, but I'll read it to you. It's called A Time for Everything. There is a time for everything, and a season for every activity under the heavens, a time to be born and a time to die, a time to plant and a time to uproot, a time to kill and a time to heal, a time to tear down and a time to build, a time to weep and a time to laugh, a time to mourn and a time to dance, a time to scatter stones and a time to gather them, a time to embrace and a time to refrain from embracing, a time to search and a time to give up, a time to keep and a time to throw away, a time to tear and a time to mend, a time to be silent and a time to speak, a time to love and a time to hate, a time for war and a time for peace. And that's Ecclesiastes chapter 3. And that's where I'd like to end.